word. You ain't never told no lie. You ain't never told no lie.
For this lesson, we're going to be finding the volume of shapes using discs, which we've already had an intro to, and washers. And we'll get to what a washer is here in just a minute. To review volume by disc, we can go ahead and take a look at this problem. We're given a curve, the square root of x, and we want to rotate that around the x-axis from 0 to 1. So this is our shape here that we're going to be rotating around the x-axis. When I rotate that around the x-axis, it's going to create this shape here. So all of our cross sections are going to be circles in this case. So using the knowledge that you already have, we know that the volume of this shape will be given by the definite integral. Our lower limit on the x-axis is 0, and our upper limit is 1. Now, for the function that we will be integrating, we want the area of a cross-section. Our cross-section is a disc in this case, and the area of that disc is given by the formula. It will have a radius that is the height of the curve, which is square root of x. So it would be pi multiplied by the radius, which is square root of x squared, and then dx. This is something that we've done plenty of times up to this point. We can simplify here. We can take the constant out, integrate from 0 to 1, and simplifying this here, it is x dx. You can go ahead and simplify that very easily, finding the antiderivative and applying the fundamental theorem of calculus. And when you do that, you should come up with an answer of pi over 2 for the volume. That's a quick review of volume by discs. Our volume by washers will work very, very, very similarly. In this example, we're going to get a little bit of practice integrating with respect to y. So we're going to have to do that when we rotate around the y-axis. We're given a couple of restraints here. We have x cubed, y equals 8, and x equals 0. When I rotate this curve here, which is the cubic, around the x-axis, we are going to be creating this shape here. Our cross sections are going to be circles. They will just be circles horizontally. So we will find the area of a cross section in terms of our equation y equals x cubed. Now we're going to be integrating with respect to y in this case. So in order to integrate with respect to y, we need our equation in terms of y. So our cubic equation would be x equals the cube root of y. That will give us the radius. You can see the radius in the picture is this distance here. That distance is the x-coordinate, which is the cube root of y. So that would be our radius, cube root of y. Now, our formula that we're going to integrate, we know that the volume of this shape is the definite integral. Now, we're integrating with respect to y, so we need to look at our lower and upper limits on the y-axis. They go from 0 to this value here on the y-axis, which is 8. We take our area formula of one cross-section, that would be pi, the radius, cube root of y, squared. And we're integrating with respect to y. Simplify this formula, and we will have the constant outside, the definite integral from 0 to 8 of, this is y to the 1/3 squared, which is the same as pi, the definite integral from 0 to 8 of y to the 2/3 dy. That's the setup of a problem using integration with respect to y and finding the volume using a disk. Doing so, you should come up with an answer that is 96 pi over 5. And that will be your volume once you anti-differentiate here and apply the fundamental theorem of calculus. Alright, now let's go ahead and take a look at some examples where we will need a washer. And we'll explain what that is here in the next. For our example for finding the volume using washers, we're going to take a look at this example that we did on the front side of your notes, and then apply the washer method because we're going to have a little bit of a different rotation. So it says find the volume of the solid obtained by rotating about the line y equals -2. So we're going to rotate this shape about the line y equals -2. Now, before I go any further, let's go ahead and think about what this shape will look like. If I rotate around this line, our value for this point rotated around will be at -4. This will be the same. Okay, our shape, when I rotate this solid here around the line y equals -2, it's going to create something that kind of looks like a bowl, but it has a hole in it. You can see that our shape has a hole right through it because there's no area in between 0 and -2. So it's going to rotate this around y equals -2, creating a hole through there. Take a look, you can see through it. A little humor for you. Now, when we want to find the volume of that, we are going to look at a cross-section. And when you look at a cross-section, say this one for instance, our cross-section has a hole in it. If I cut this shape in half and look at the face and see what it looks like, our cross-section has a hole in it. So what we're going to have to do is we're going to have to think about the area of this cross-section. It's a washer. It looks like a washer, that's why we call it the washer method. It is a disc with a hole in it. So if I want to talk about the area of this, I know that I'm going to take the total area and subtract out the area of the hole. And then we'll integrate similarly to the way we did when we were finding the volume using discs. So, the total area of this shape, before I subtract out the hole, the total area is this distance. Here's the center, and it goes up to the curve. Now that distance is the value on the curve, which is the square root of x, plus this distance here, which we know is 2. So this total radius for the total disc is 2 plus the square root of x, or the square root of x plus 2. That gives us the total distance. Square root of x plus 2 is our radius. Now, that's not the area of our circle because we have a hole in it. So we're going to end up having to subtract that value out. Before we do so, think about what the radius is of the hole. That is a constant. It does not change. The radius, no matter where we're at, is 2. That is our radius. It is 2. So, if I look at the area of this disc, we can take the total area. So our area in terms of x is the total area, pi, the radius, square root of x plus 2 squared. Pi r squared, that's the total area, minus, we're going to subtract out the hole from the washer, pi multiplied by the radius squared. That is a constant. Take a look at what we have now. Our area of our cross section is the area of the total, the large radius, minus the area of the smaller radius. And we will go ahead and integrate that from our lower limit of 0 to our upper limit of 1 in this problem. So doing so will give us the volume is equal to the definite integral from 0 to 1 of pi square root of x plus 2 squared minus pi multiplied by 4. 2 squared 4. Simplifying. You can simplify this using your properties of definite integrals. If you want to integrate this one separately from 0 to 1 and integrate this one separately from 0 to 1, that is fine. If you want to simplify in here, that will work as well. If I think about simplifying inside here, I know this is equal to 0 to 1. If I factor out a pi, it would be the square root of x plus 2 squared minus 4 dx. And then we can integrate from there. This is something that you know how to do. The setup is the new thing. The setup is volume using a washer method. Take the outside minus the inside for your area of the disk, and then we'll integrate from our lower limit to our upper limit. Moving on to example 3. We're going to find the volume of this shape rotated around the x-axis. We will see that it will need to, we will need to use the volume by washer method. Let's go ahead and take a look at what the shape will look like. You can see that it's kind of a bowl with a triangular shape in the middle, kind of a bowl with a cone right in the middle of it that's open. So if I think about a cross section at any point inside this bowl, it's going to have a hole in it. So, doing so, we can think about the disc that we have. It is a washer. We have an outside radius, or the total area, and we also have an inside radius, which is changing in terms of this problem. If I look at the outer function, cross-section, the hole inside is much larger than it was here. So we know the size of that hole inside or in the washer is changing. It is a function, so we'll have to label it as a function. So let's take a look at the outside curve. In this shape, we can see that the outside function, if we rotate it around the x-axis, the radius of the outer disk, in terms of this disk here, is the height of the top curve, which we know is first quadrant closed with y-axis, cosine, sine. Alright, so the outside curve is cosine. So this radius is given by cosine of x. So the outer function, or the total for the disk, is pi multiplied by the radius cosine of x squared, pi r squared. Now we need to subtract out the inside function. Subtracting out the inside area. Well, the radius of that area is changing, as we said earlier. We know it's given by the sine function. The radius is the sine of x. So we're going to subtract out that area. Pi sine of x, that is our radius, squared. This gives us the area of a washer at any point x throughout our upper and lower limits of integration. Plugging this into our formula, we can see that we are going to integrate from 0 up into the point where they intersect. Now, you knowing the unit circle very well, you know that sine and cosine are the same or equal at pi over 4. So we are going to integrate to find the volume from 0 to pi over 4 of this function. If I factor out a pi, it would be cosine squared of x minus sine squared of x, and that is dx. This is the setup of the problem. Now you'll go ahead and use your rules that you already have for antiderivatives and the fundamental theorem of calculus to evaluate the definite integral. When you do so, you should come up with an answer of approximately, or exactly in this case, pi over 2 units cubed. And that is finding the volume of a solid using the washer method.